Hello everyone and Happy New Year. This is Rona from eMaint Enterprises, and I'd like to thank you all for joining us today. I'd like to thank Jeff for being with us today. And Jeff is a CMRP and CPMM and is a managing principal for People and Processes, and he's really educated hundreds of different organizations and clients in educational, manufacturing, municipal, and facilities environments to help them improve their practices. He's also certified in maintenance best practices and is an RCM2 practitioner. And Jeff is a frequent speaker at maintenance conferences, and you've probably read many of his articles and blog postings. And he also leads many of People and Processes core training classes, such as maintenance planning and scheduling, maintenance reliability for managers, supervision, and RCM2 classes. So Jeff, thanks again for joining us and taking time out of your busy schedule to put this together for our group.
Well, thank you so much, Rona, and I really appreciate eMaint offering the opportunity for us to share this knowledge with everyone in the audience too. So today we wanted to really talk about learning the secrets of great PM programs. And in reality, a lot of things are really not that secret, but it just happens that we haven't taken the opportunity to apply those to the PM programs we have. So if we talk about the realities of PM programs, and we were talking earlier as people were signing on about that some people believe that 62% of the overall population across the world either does not have a PM program or is in the process of building one. And if you look at the realities of a PM program, ideally what we want is we want 100% completion. And actually from a world-class perspective, from a metrics perspective, we evaluate that using a term called PM compliance. And we're always looking for at least 95% PM compliance. Reality is, though, is that only about 60% of the PMs that we trigger and schedule out every week, every month, every quarter, whatever the case may be, only about 60% are actually done and turned back in as completed. Now, of those, really only about 20 to 30% are done properly. And so it highlights some significant issues with regard to the PM tasks that we have. And if you ask, okay, well, why, Jeff, do we have just 60% done? Well, part of it is in many cases, and I work with some organizations that really struggle with this, the PM task will identify to do certain things, and that piece of equipment may very well have even been removed from the system and is no longer there, but yet the PM task is asking them to do a specific thing. In addition, that you'll also see PM tasks that are non-value added, and the maintenance technician looks at it and says, that's just a waste of my time, so I'm not going to do it. Or if they possibly don't understand the reason for doing it, they'll not do it. And then, of course, we've got the training issue with regard to the 20 to 30% done properly. So let me ask this question. What percent, well, we'll do a poll question, Rona, and around more PM, for example. And what I'm looking for here is the amount of what do you believe that the percent of failures that are random as opposed to reaching a wear-out zone? So what do you see as a end of life? Do you think all equipment reaches a wear-out zone or an end of life? If you'll post that poll, Rona.
Okay. So I just launched the poll, and again the question is, what percentage of failures are random as opposed to reaching a wear-out zone? So if you want to indicate in your responses, I see some of you typing in, and we're saying, do you think it's 20% of your failures are random, 40, 60, 80, or 100? All right, so we'll leave this open for maybe about 10 more seconds while your answers come in. And I can see everybody continue to type. Okay, we have about 80% of the votes in. A couple more seconds here. Okay, I'm going to go ahead and close this, and let me share the results. So Jeff, what we found was 20% of the audience felt that the failures are random. I'm sorry, 43% of the audience felt 20% of their failures are random. 16% felt it was 40%. 22% of our audience felt it was 60%. 20% of our audience felt 80%. And nobody said 100, so that's a good thing.
But you know, Rhonda, one of the things that's scary about that, and this goes to show how we haven't done a good job communicating out to the maintenance profession how failures really occur. And that's one of the intents of the webinar today. So I'm going to hold the answer to that question for just a minute, and I will go through this slide, and we're going to come into how equipment fails in a later slide, and I just want to say the answer to that. But it was interesting that by far the majority said it was, either 20 to 40% of all failures were random in nature, as opposed, and even up to the 60%, and there was only, like I say, 20% of the audience that believed it was 80%, as an example. So let's hold those numbers and let's continue on with this. In the 1960s, if you look at the airline industry as an example, we were having 60 crashes for every 1 million takeoffs. And it's hard to fathom that today, knowing what we know. Basically, that would be the equivalent of 2 complete 747 crashes per day. And when we talk about risk, I don't think many of you would be willing to get on a plane today if you saw the issues with regard to the potential for crashes. 2 out of every all the planes that take off every day. So if we look, what was happening is that they were doing overhauls, or what we call scheduled restoration, at 6,000 hours. So with these 60 crashes per million takeoffs, the FAA got involved and everyone else got involved, and they said, hey, we've got to reduce this, obviously. So let's change, and we'll do maintenance instead of at 6,000 hours. We'll do these overhauls at 4,000 hours. And what happens is that's actually 50% more maintenance. What do you think the result was? Well, what actually happened is we didn't really reduce the amount of crashes at all. And, if you ask and say, well, the manager's happy. Well, the managers weren't happy because we were taking, the planes were no longer available to fly, and because we're on the ground doing much more maintenance than we'd previously done, 50% more maintenance, and we hadn't impacted that at all. So now what we started doing is we moved into the realm of reliability-centered maintenance, and now we have 0.1 crashes per million takeoffs. And while obviously in the 45-minute webinar we can't talk about all the things with regard to reliability-centered maintenance, we are going to talk about certain parts and pieces of that as related to PM tasking from pretty much an everyday standpoint. So if we look at the traditional view of maintenance, what we have is a belief that most items fail around some particular mean time before failure. So as you rock on and you reach a wear-out zone, you see a greatly increased frequency of failure, or conditional probability of failure, if you will. And we back up about 66% of that mean time between failure and say, okay, that's the useful life of the equipment. And what we do is we set up our PM programs to basically take that into consideration. So what we do is we do scheduled overhauls and scheduled restorations and scheduled discards, as opposed to doing condition-based activities. And if you think about it, really, about 85% of all maintenance done today is done in this traditional fashion. About 85%. So if we look, with regard to maintenance cost, your most expensive maintenance that you can do is break down a reactive maintenance, where we run things to failure. And when we do that, we incur the downtime losses associated with losing the equipment, as well as the cost to repair. In addition, we often have collateral damage, we'll call it, where instead of just losing a bearing, for example, on a pump, we might lose the bearing, the shaft, the impeller, the housing, and all of that due to the damage that comes from the running to failure. Now, if you ask, is run to failure, or should I say no scheduled maintenance, a viable alternative? Yes, it is. Okay, it is part of your strategy, but it's also not the dominant strategy that we should be using either. And if we look at time-based PM or overhauls, what happens is that's your second most expensive maintenance, and there are many organizations today that still use that as a primary means. As we said, 85% of all maintenance is still time-based, and your least costly maintenance is condition-based maintenance. And with that said, we'll launch this next poll, Rona.
Okay, I'm going to launch it now. So the question, I guess, is what percentage of your PMs are scheduled or time-based restorations, overhauls, or discards? So Jeff would like to know, I see the votes are being cast. Is it 0 to 20% are time-based, 21 to 40, 41 to 60, 61 to 80, or 81 to 100% time-based? All right, so I see about just over half the votes are in. So we'll leave this open. And again, what percentage of your PMs are time-based versus condition-based or the other methods that Jeff alluded to? All right, we're 80% in. A couple more seconds here. Okay, let me close it and share what we have. All right, 14% of our audience says it's less than 20%. 5% say 21 to 40. 16% say 41 to 60. 21% say 61 to 80. And then 44, or nearly half, are saying over 80% of their PMs are time-based. All right, Jeff, so I'm going to hide this and turn it back to you.
No problem. Thank you, Rona. And that just validates what we just said with regard to 85% of all maintenance is time-based. Now, let's look at how equipment actually fails. And this comes from the Rowland and Heaps RCM study that was done in the 1960s and validated again in the 1970s and again in the 1980s. And it was also part of the RCM2 work that John Mowbray did, and they converted it from the military and aviation over to industrial components. And what they found was very similar numbers. And so if you look, the very first A curve that you see there, what we're looking at is on the left is the left scale is conditional probability of failure. And what you have is this is what we call the classic bathtub curve. And up until, well, around the 1960s, late 1950s, early 1960s, we actually integrated the very first part of this curve in to include infant mortality. Right? And then you have just a random rate of failure, and then you reach a wear-out zone. And then if you look at the B curve, it has no infant mortality, and then just a wear-out zone, okay? And when we talk about a wear-out zone, what we're talking about is a repetitive mean time before failure. So a repetitive number of samples have failed around a certain time, which indicated a wear-out zone. And so A, B, and C have an end of life, if you will, or a wear-out zone. And C just slowly increases over time. But if you look on the right side, what you see is you see that you have a rapidly increasing up to just a random level of failure, and then it's just flat after that with regard to the D curve. And E is just totally flat, meaning totally random. And F has an infant mortality, and then just totally random. But more importantly, look at the numbers, the percentages to the right of each curve. And what you see is that for age-related failures, we only have 11% of failures have a pattern which indicates that there's a wear-out zone. And 89% of components actually have no end of life or no wear-out zone if they're properly maintained. And if you look at E, for example, E is actually the failure pattern for bearings, for roller bearings, ball bearings, those type things. And if a bearing is properly installed and is properly lubricated and it's not overloaded, then it just has a random failure pattern. So when we talk about that 85%, if you notice, we're doing all this work over here that's 85% on the left-hand side of the chart, time-based. But reality is when you slice that, okay, based on buckets of time, once a week, once a month, whatever you're doing your PMs at, it won't catch the problem because the problem is random. 89% of the failures are random. Okay? And so that's why time-based maintenance is not the best solution for you. And this is one of the great learnings from RCM. So when we look at like mean time between failure,
Sorry, Jeff, are you there? I think we've lost the audio.
okay, I'm back.
Okay.
I'm sorry. So what I was saying is if you look at the failure times, 180 days and then 212 days and 940 days. And so we had 32 days between each event, between the first event, 728 days between the next event. And you add those up and you divide them by the number of events, and that gives you your mean time before failure. And so if you look here and you say, okay, if I was doing a time-based pattern, what time-based pattern could I use? If I was looking at, say, for instance, every 340 days, would I catch the one at 728? No, I wouldn't. And I would miss the one at 510 days. See, so this is a perfect example of why time-based maintenance is not the best solution for the majority of your failures. And furthermore, if you look at the 32 days and the 40 days as compared to the rest, what that suggests is infant mortality. And infant mortality can come from several different things. It can come from improper installation methods. It can come from improper training. It can come from inferior parts. If you think about what's on the storeroom shelves, they may have been there for years and exceeded the shelf life. Even a bearing has a shelf life with regards to the lubricant drying out and false spinelling occurring while it's sitting on the shelf. So all these things you need to take into consideration, but again, time-based maintenance only works when we have a repetitive mean time before failure. And we can come back to that and know that, okay, the useful life is some percentage of that, and we do the schedule overhaul, schedule discard at that particular point and restore it to usable condition. So, and again, I wanted to point out that only 11% of all items, all components, had a wear-out zone. See, so that's, again, this points to not using time-based maintenance. If we talk about failure management strategies themselves, we have basically two time-based strategies. One is schedule restoration, and the other is schedule discard. And if we look at schedule restoration, it's overhauls. And I'm really trying to get you to use these terms as well. So schedule restoration could be an overhaul. It could be just simply restoring lubricant back to a bearing inside of a pump. So we're doing the schedule restoration of the lubricant inside the pump so that it'll continue to eliminate friction or wear. Schedule discard is where we change the fluid out. Maybe we change the oil in the car, as an example. And then on-condition task. An on-condition task takes the form of two different things. Either the use of predictive technologies like vibration, infrared, ultrasound, oil analysis, all those other technologies, or simply just looking for it in the act of failing. Okay? And it's an important piece to mention here too, with preventive maintenance, the fixed interval, what we're doing is we're replacing parts whether they need to be replaced or not. We're doing it on an interval based on time. So when we do an overhaul, we're replacing everything, whether it needs it or not. And at the same time, we're introducing the opportunity for infant mortality simply from poor maintenance practices. And there's a statistic out there that says up to 70% of maintenance failures are self-induced. As I mentioned earlier, from training, parts, installation, poor purchasing decisions, on and on and on. So every time, and it's intrusive, so every time we do intrusive maintenance, we offer the opportunity for failure. And on condition tasks, what they're doing, the predictive technologies, we're monitoring it over time. The same thing with the condition monitoring tasks, just a human inspection. Is it making more noise than it was last time I checked? Or is it hot to the touch? Or anything like that. And what happens with that is now what we're looking for is we're looking for things in the act of failing. That's what we're after, are things in the act of failing. And do we have, if we find it in the act of failing, we want to put a work order in to proactively plan and schedule the repair and execute it before it functionally fails. And we'll talk about functional failures a little bit later. But the third option is no scheduled maintenance. And we talked about that a little bit earlier. That's not the same as run to failure. No scheduled maintenance says that we're not going to do an overhaul, as an example, because maybe there's non-operational consequences. So we'll run it until it fails. Maybe if we have a standby pump. If we have a duty in the standby pump, as an example, we'll run the duty, do no scheduled maintenance on it other than basic lubrication task or basic maintenance. And then once that pump fails, we'll switch over to the redundant pump, standby pump, and run it and repair the duty pump. And then with number 4, you have one-time changes, and those are related to either the maintenance procedures themselves. Maybe it's an engineering change that we can't fix it from a maintenance or operations procedure standpoint, so we'll redesign the equipment. That's an option for us. The other thing would be something like an operations procedure change, or a checklist or whatever. And people always ask to say, Jeff, where do we start? I've always heard that we want to do it based on criticality. And if you're doing a new site, criticality is a great way to do it. But if you've already got equipment in place, you think about it, most people already understand what your most critical pieces of equipment are, and you're already doing tons of maintenance activities around that. You may even have service contracts on it, for example. But where I encourage people to focus on with regard to optimizing their PM program is, where are you bleeding? Where are you hemorrhaging the most money, the most downtime, the most maintenance hours, the most spare parts cost? Those are the places that you need to focus on first and need to optimize, because, again, that's where you're losing your money and you're losing your production capabilities. So focus there. And borrowing from the RCM piece, what we're really after is to determine what are the actual failure modes of the equipment. And to do that, we want to understand first, what is the function of the equipment? The very first primary function of a piece of equipment, for example, is what we bought it for. And in this particular case, we may have a pump. And the sole purpose that we really bought that pump for was to be able to transfer water from tank A to tank B at a minimum rate of 75 gallons per minute. And then we have functional failures. And we may have multiple functional failures for any given function. And typically you have a partial failure and a total failure. So if we look at, in this particular case, we started with the total failure, and it's unable to transfer water at all. And there are failure modes that are associated with being unable to transfer water at all as compared to being unable to transfer water at a minimum of 75 gallons per minute, which means partial failure. So we have total failures and we have partial failures. And if we look at the failure modes for those, if we look at the one for unable to transfer water at all, well, the pump bearing seized due to improper lubrication. And then we can figure out how we can address that from the PM task, condition monitoring task. We might use vibration as an example to find out if we're properly lubricating the bearing, or many different options that we can use. And then for 1B1, the impeller warn is we're able to pump, but we only have a partial failure, and we can't meet what their user requirement is. Their requirement is 75 gallons per minute. We may be pumping at 60 gallons per minute. We haven't totally failed, but we're not meeting the user requirements. So we determine our failure modes, and from our failure modes, we determine our task. So if we look at the failure modes, here's some examples of failure modes. And there are lots of different, and it's all related really to your operating context. And that pops up here. You can't take, people say, well, I'm just going to take this off the internet. I found these failure modes, and I'm going to take them and I'm going to use them in my PM program. You can't do that. What happens is your operating context, you might be pumping concrete where I'm pumping water with the same pump. So my failure modes might be very different than your failure modes. So again, operating context plays into that. Rhonda, we've got another poll here, and so I'll let you hit that.
Okay, so let's go ahead and launch this next question. What is the basis for your PM tasks and scheduled frequency? And in this one, you can select all that apply. Are you basing your frequency of PMs on the OEM manual? Are you basing it on failure mode analysis? on equipment history, or what Jeff is terming tribal knowledge, or just sort of collective knowledge. All right, so again, what is the basis for the frequency upon which you schedule your PM tasks? OEM, failure mode analysis, equipment history, or tribal knowledge? Right, it looks like we have about 2/3 of the vote in. We'll leave it open here, a few more. Oh, it seems that, sorry about that, I might have set this up that you can only select one. My apologies. So if you don't mind, tell us what you think the majority of your PM tasks are set for, if I didn't make that multiple choice. Okay, looks like everyone has voted. So let's share the results. And Jeff, it looks like 39% say OEM manual, 9% utilize failure mode analysis, 23% equipment history, and 29% tribal knowledge. So equipment history and tribal knowledge are about half, failure mode analysis a little below 10%, and the manufacturer specs close to 40. All right, back to you.
Thank you so much. And you know, I was actually working with some OEMs just in the last few weeks, and we were going through an introduction to RCM2 class with them, and it's really scary because they don't have the information themselves, because they can't get it from the vendors that they do business with. So, for example, like for hydraulic pumps and other things like that, they're doing their best guess, and again, they don't have the data, and they don't have the data coming back from you as a customer in some cases to be able to quantify that information either. So it's interesting that we focus on the OEM manuals, which in turn, all they're doing is almost like tribal knowledge to a certain degree amongst themselves to figure out what the right answer is. So the message for OEM manuals is this: we need to use those as a guideline, a starting place, but we need to combine. Obviously, the most effective method we can use is the failure modes themselves, but equipment history is very vital to that too. And even when you're doing failure mode analysis and you're stepping through from an RCM analysis perspective, you combine all of these things. You combine the OEM equipment manuals, you combine the equipment history. Has it ever failed before? How many times has it failed? And you combine the tribal knowledge of the people, and they're actually sitting around in the room as part of the analysis process to help you come out with the best possible task. But ideally, really where you want your basis is your failure mode analysis, or RCM, or maintenance task analysis, is your most effective, cost-effective method. And if you think about the PM tasks that we do you realize that about 40% of PM tasks that we have out there now are non-value added? They're non-value added. And we ask people to go do it, and that's maintenance labor that we could be doing for other things. And most organizations that I go to, they tell me, Jeff, we don't have enough people. We don't have enough hours in the day to do all the things we need to do. And as part of that is because we're doing non-value added PM tasks as part of that as well. And I wanted to go back and answer the very first poll question, because we put it up there and it was 11 to 89%, with regard to 89% being random. And what we do, just from a simple, because it varies from industry to industry, but on average, what we simply say is 20% time-based and 80% random. Okay, so I want to come back and cover that. So if we look at the RCM Logic Tree, and you guys can Google the RCM Logic Tree and actually find many examples out there. But basically, what happens is depending on, regardless of whether it's a hidden failure, and we're going to talk about hidden failures a little bit later, or a safety environmental, or an operational consequence, or a non-operational consequence, it still follows down. So we kind of go across the chart and say, is it safety and environmental first? And if it is, then the very first thing we want to do is develop a condition monitoring task. And if that's not technically feasible and worth doing, then what we want to do is develop a time-based task, a scheduled restoration, or a scheduled restoration, or a scheduled discard. And that has to be technically feasible and worth doing. If we can't do that, then we either have to redesign the system, and in the safety and environmental issues, that's a compulsory obligation, okay? Where in operational and non-operational, that's not compulsory, and it's up to us to decide whether we want to accept the failure risk. We can't do that from a safety and environmental perspective. And then the fourth option is we can just, as we said, accept the risk and run it till it fails, and that's a very viable strategy. If we took the sprinkler system that irrigates the front yard or whatever the case may be, we're not going to do a lot of maintenance on that. We're not going to do condition monitoring or anything like that. When the sprinkler head fails, we're going to go out and we're going to fix it. We're not going to invest money to go out and PM the sprinkler heads. So that's a good example of things that we run to failure. But the logic tree, again, if you step through it, it always starts with condition monitoring, regardless of whether it's health, safety, and environmental, hidden, operational, or non-operational task. It always starts with condition monitoring because that's your least expensive, and the goal is you're trying to find things in the act of failure. And then next to the scheduled restoration or scheduled discard, which is your next most expensive maintenance. So we talked about doing one-time procedural changes, which was basically the same. When we selected something like no schedule maintenance as an option, that doesn't mean we can't make a change to a procedure. So you think about what happens with your operation side, your startup and your shutdown checks, your cleaning procedures, any of the operations procedures with regard to how they run the machine, any kind of visual aids that you can add, for example. Like a green transparent film over a pressure gauge to indicate that this is the zone that should run in, and if it's in the red area, it's not where we want to be. And same thing for maintenance procedures, not just the PM task itself, but also maybe a job plan with regard to how we plan and schedule work and do the corrective action itself for the repair. And then as part of the one-time procedural change, we can also do engineering redesign. When we look at the PM itself, in the PM task, what we're really looking for is standard procedures or standard work, and we're looking for precision maintenance. And we'll talk about precision maintenance in a minute, but standard text, any kind of lockout, health, safety concerns, disposal issues, anything like that, we want to make sure we have it in the PM task. We want to make sure we've got ergonomic hazards with regard to lifting or bending or whatever it may be. We want to make sure we've got the procedures, and again, into a detailed level, and tack times for those. Tack times are simply how long we should estimate it to take to do the work. Now, people get upset about tack times, but the intent is we've got to be able to estimate from something how long the job's going to take. So what we do is we break that down by procedure. By each step of the task, each task step, we add minutes to that and say, okay, and then we total those up at the end and say, okay, this is a 3-hour job. We don't really want to get upset if for some reason those jobs take longer than 3 hours, because sometimes they do. We get into a job and we realize, hey, we're going to have to do this, for example, that we didn't plan on. Maybe the bolts are rusted and we've got to cut them off, whereas 6 months ago we didn't have that problem. So, you know, it's okay if they vary, but if they, for example, if you get in and you're doing a PM and you realize that the piece of equipment is going to take longer to fix because it has more damage than you originally might have anticipated, then you really should write a separate work order for that if it's more than about 30 minutes. And you write that as an emergency work order to cover that time that was outside of the scope of the initial PM. And one of the things that we want to make sure we get back from the crafts is feedback. You know, what are you finding? Do we need to come back and do additional work on this? Do we need a second work order or a follow-up work order? Should I have parts to you, for example, as part of the PM, so that I can go out there and do everything I can to do the job right the first time without having to close it back up unfinished and come back to it later. And then we even want consumables, materials, and any kind of special tools or rental equipment that's required. That needs to be part of the procedure as well. If we look at that standard text, what you typically see is lockout, tagout, check belt. Well, if I ask anyone in the audience, I can get one answer for check belt. If I ask someone else in the audience, I can get another answer for check belt. And, you know, what do we really mean? And the same thing for check auger. And so what we're looking at is something that's more descriptive, like what you're seeing now on the screen, which is lockout, tagout. Okay, well, install lock on auger disconnect 54 and lockout air valve at column G34. With regard to check belt for discoloration, wear, and cracking, adjust the belt tension between 4.4 to 5.7 pounds using the spring tension gauge. Again, we're looking for precision maintenance, not just the old thumb trick. And check auger shaft as an example. So here you've got clearances and fits and torque as an example. So again, we're looking for precision maintenance. And with regard to lubricating bearings, notice it says 0.2 ounces. Well, how would you know that? You actually calibrate your grease guns. So you know that so many shots equals so many ounces. And that way, and you can, from SKF, for example, you can get a CD that says, okay, for each particular bearing, this is how much lubrication you should be applying to it at what frequency. And you don't pump till you feel pressure, as an example. Grease gun's a deadly weapon. It can generate 10 to 15,000 pounds of pressure. So it blows your seals out if you do that. So we want to add just enough lubricant so that we still have enough room in the bearing for the lubricant to expand without blowing out the seals. So talking about precision maintenance, and I mentioned that a little bit ago around like torques and fits and that type thing. How many of you use shiv gauges as an example? You see a picture of a shiv gauge there and seeing how much clearance you have between the gauge and the actual shiv. And torque ranges and tolerances and those fits, that's the information we want so we can set things to a precise level every time we do the work. And this particular thing you're seeing here, if you've never seen this, is called the PF curve. And what happens is I don't think you'll be able to see my mouse, but you have some event, and what happens is you can detect the potential, if you will, for failure after that event happens. Maybe, well, I happen to work with mining groups as an example, and they're large mining groups, and they're mining where they have coral heads, and they're surface mining. And what will happen is they're pulling with water. They're transporting the rock aggregate with water, and they'll have a coral head that actually goes through the pump, as an example, and damages the pump. So here's a perfect case where you had an event, and now you have the potential for failure. And we can detect that using many different things. It could be a flow meter, it could be a valve, but anything. And what you see is the minimum process requirement here. That's the want of the user. So maybe that's 300 GPM. And the line over there on the left where we started out with the pump, started out the curve, maybe it's 450 GPM if you could visualize that. And what happens is we introduce that potential for failure. That means we're starting to drop off on the flow. So we've gone from 450, we might have gone to 360 or whatever the case may be. But once we reach 300, which is what the user wants, we're no longer meeting the expectations. Well, if we go to 299, for example, 299 gallons, we're no longer meeting the expectation of the user. So that's what we call a functional failure. And with regard to functional failures, let's say that's a partial failure. Where down at the bottom, you have a total failure, unable to pump at all, or unable, with regard to the functional, unable to pump 300 GPM. So what we want to do is we want to find things in the act of failing and proactively plan and schedule the repair before it functionally fails. Right? And if you ask about setting the frequency, what happens is if you had no other information, your initial interval that you would set would be half the PF interval, would be 1/2 the PF interval. Okay? So got another poll there, Ronna?
Okay, let me go ahead and launch this for you. So based on studies, Jeff is asking what % of protective devices are already in the failed state right now? All right, so if you'd like to cast your vote, do you think it's 20, 30, 40, 50, or 60% of protective devices are right now in the failed state? All right, so if you go ahead and give us your view based on studies of what you believe the percentage of protective devices that are currently in the failed state. Looks like we got about 2/3 of the votes in. And I think people are having to think about this one a little bit more. All right, we're at 80%.
I should probably say
leave
the
it
protective
open.
devices. I'll go ahead. Yeah,
No,
sorry.
go ahead. Maybe you'll influence some answers.
Well, we're okay. I should have prefaced this one with a thing, and I apologize to the group, but I'll cover it in just a minute, so it really you won't miss it. But I should have prefaced the whole question initially.
Okay. Well, what our group has told us is 42% say 20% of devices are in the failed state. 34% say 30% of the devices are in the failed state. 8% believe it's 40%. 11 say it's 50%. And 6% say it's 60%.
And
right.
so your largest number was 30%, Rona?
Was actually 20% was the largest, and followed by 30.
Okay, all right, no problem. Good. That's scary, and we'll talk about that in a minute. So with regard to PMs, I've got to speed this up a little bit since I know we're getting close on time. I want to be able to answer some questions. One of the challenges for us is we need to make sure we inspect. We get what we inspect. If we're not inspecting, if we're trying to manage from behind a desk, we can't do that very effectively. We need to measure, and then we need to audit. So we take 3 PMs out at the end of the week or the end of the month. We take the maintenance manager and the operations manager, and we go look and say, okay, what worked, what didn't. And we're not so much focusing on the actual work itself, but did the processes associated with it work. So to measure the value, one of the things that you need in your CMMS is corrective repair from PM or PdM or CBM. And what that tells us is when we did the PM, did we find anything from it? Okay. And in many cases, many CMMSs, people don't add that code, and that's very important. We want to determine the value of the PM program, so corrective repair from PM or condition-based maintenance. And then you have other performance indicators, PM and PdM effectiveness, mean time before failure, mean time to repair, that should be MTTR. And PM compliance, unplanned versus planned, or planned versus unplanned. How reactive are you? Ideally, you should only be about 10% reactive. And we talked about rework earlier. One organization I worked with, they were only measuring rework out 48 hours, and they didn't start the lineup for over 48 hours. So they never had any rework. And the maintenance manager was really proud of that. And I said, well, okay, but you had a failure over here. How long has it been since the line started? Well, I said it's been, 60 hours, but that was outside of our 48-hour window. Okay, well, not a good answer. So we want to focus on continuous improvement. We develop and we load the PM task. We schedule those inside the system, which triggers, and we work level those. We execute the job. We get closing notes or feedbacks from the crafts, and then we improve the PM, and we continue the cycle. Hidden failures is what we started to talk about with regard to the poll question. It really relates to protective devices. If one of the questions in RCM is, will the functional failure on its own become evident to the operating crew under normal circumstances? And let me show you this example. We've got a level transmitter in this silo or this tank, and what happens is the level transmitter is it's an ultrasonic, and it's controlling the level using the programmable logic controller between 5,000 and 9,000 gallons. Okay? And the operator normally sees that. Okay? Now we have a high level that sets the trips at 9,500 gallons, and a low level that trips at 4,800 gallons. And the question is will the functional failure of the high level or the functional failure of the low level on its own be evident to the operator under normal operating circumstances? And the answer is no. Okay? So you could actually fail either one of the switches at the top and the bottom, and the operator may never know that because the level's being controlled separately. And you can think of it almost as your spare tire in your car. You've got the tires on the outside of your car that you're rolling on now, and you've got your spare. And unless you've got a pressure sensor on that tire, without going and doing failure finding activities to see if it's failed, you would have no knowledge that would have failed on its own. And so what happens is you might have what we call a multiple failure. You lose one of the tires that you're riding on, and you go to get the spare. So that first tire failed, you go to get the spare, and the spare is not available for you because it's already failed. We call that a multiple failure in RCM. So when we talk about hidden failures, that's what we're talking about. And so if you think about protective devices, which in some cases are hidden, they warn operators of abnormal conditions. It could be a sign, it could be a light, it could be a horn. They shut down equipment in the event of a failure. It could be a relay. They eliminate or relieve abnormal conditions caused by failure. Might be a pressure relief valve. or they take over from a function that has failed. Might be a standby pump as an example, for taking over from the duty pump, or they prevent dangerous situations from arising. A guardrail is a good example. So not just instrumentation, but even things like guardrails or signs on the elevator. If you think about in a hotel, don't ride this elevator in case of fire. Use the stairs instead. That's actually a protective device. And how many protective devices do you have? How many do you currently maintain? We've already asked this question. I thought I might have had too many poll things in there, Ron, so disregard that one. It's based on, if you look, many cases we don't realize how many protective devices we actually have in the organization. And these are the things that are really going to bite you when it comes back, because they're the kind of things that you're relying on to save people. So when we talk about that, things like emergency stops, pressure relief valves, ruptured disc, even if you take your smoke detector or that spare tire. So if you think about it, how many of those are you really maintaining? And the scary part is there's probably 40% in your factory that you don't even maintain, and there's probably another 40% that you don't even know about as part of that. They're even there. So that's it. I wanted to mention some additional, well, I'll hold off there for a second, continue on just a minute with the hidden piece. Be sure to consider the hidden failures inside your organization and your protective devices, because those are safety things that you might not have visibility to unless you do a failure finding activity. In other words, you go looking to see if that actually is operating. So upcoming educational opportunities, there's a great opportunity in Atlanta. We do a 4-part series for maintenance and reliability for managers. We often have planners in there, operations managers. It basically is, you go for 3 days, and then you leave for 2 to 3 months. You go back and work at the site, and you come back for 3 more days. And you do that 4 times across a year, 8 months to a year. And the first course starts, and the first week of that starts February 7th through 9th in Atlanta. And then there's also, we talked a lot about RCM2. There's a 3-day introduction to RCM2 class that we teach, and it's actually, we're part of the Aladdin Network, and that starts February 21st and 23rd in Atlanta. Well, thank you so much, Ron, and thanks to everyone for allowing me the opportunity. We really do enjoy sharing with the community. And you can go to the People Processes site. You can also go to jeffshiver.com, where there's a blog, and maintenanceplanningendscheduling.com, where there's a blog. And we run many different things, LinkedIn, and like I say, you can send Tammy Pickett a note, and she'll tell you all the different places that you can find information that we put out for everyone's use. So thanks, Rhonda, for having us, by all means. And thanks to everyone for attending.
Okay, and we'll see you all next month, guys. Thanks again.
Bye-bye.